and I'm going to talk about my honor thesis project, a testbed for evaluating and visualizing Facebook friend list recommendation. And my advisors are Professor Prasun Dewan and his PhD students Jacob Bartel. So by friend list, I mean reusable named groups, so which allow users to manage their friends into groups and perform group-specific sharing. So, but there's a problem with the reusable friend list is that people do not take the effort to create the friend list, but they want the group-specific sharing. And so, as computer scientists, we want to help users to reduce the effort to create friend list. And recently, there has some work on this topic. For example, it's Professor Dewan and Kelly Bacon's algorithm. So since we have had this algorithm, so the problem I want to solve is that, so how can we evaluate these algorithms? So this is my approach. So I want to create a Facebook testbed that allows recommendation algorithm to be empirically evaluated. So the testbed consists of 3 components, and here is my workflow. So the first part of the system is the Facebook recommendation engine that collects users' social graph and generates the recommendation result. So after we get a result, we go to the second part. It's a friend list editor for the end user. It allows users to edit via the recommendation result. And the third part of the system is called the performance and visualization tools. So we designed this tool for researchers to evaluate the result and the algorithms. So let's start with the recommendation engine. So the recommendation system is a Facebook web app that mines the user's social graphs to make predictions on friend lists. So it first asks users permission to collect their social graphs. So we keep all the data anonymous in the secure folder in our department server. So after collecting the social graphs, the recommendation system runs 2 recommendation algorithms. So the first algorithm is a group recommendation. So I use the hybrid click merger algorithms. This algorithm is developed by Professor Dewan and Kelly Bacon. So the algorithm analyzes the user's social graph and tries to find the maximum clicks to derive the recommendation results. So here is the detail of the algorithm. So the algorithm tries to recommend friend list based on the user's friends and the connections between friends. So the algorithms analyze the social graph to find the maximum clicks and use the clicks to derive friend list. And the click is actually a set of nodes in a graph that all members are connected to each other. So for example, in this graph, so Alice, Bob, and David, so they are all connected to each other. So so they can form a clique. And so this clique will later be combined with other cliques that overlap with it to form the recommendation result. So the second algorithm the engine uses is called evolutionary recommendation. So this algorithm is developed by Jacob Bartel. And in this algorithm also uses the hybrid click merger algorithm to generate the recommendation result for both the old social graphs and the new social graphs. And then it tries to match the groups in the old recommendations to the newly recommended groups. And then it can form the evolutionary results. Okay, so let's go to the second part. It's a friend list editor. So the friend list editor is also a Facebook web app that allows editing recommendations and measures the effort the user takes to create the friend list with and without the recommendations. So it has 4 steps: undirected creation, recommended addition, directed creation, and the post-study questionnaire. So I'll introduce the detail in the demo in the next slide. So here is the demo of the editor. Now you'll say it's an introduction page. And then we enter the first step. So in the first step, the undirected creation, we want the user create some some lists manually without our direction. So for example, I just create a list called UNC Chinese friends. And then I select all my Chinese friends at UNC from the left column and where all my friends are listed there. So after finish selecting, I just add them to the list. And then we go to the next step. So we ask you, in this step, we ask you to view, edit, and rename the recommendation results. So for example, I thought this list makes perfect sense to me because it only contains all my friends from University of Wisconsin. So I will set the list and then rename it, and then I publish the list to my Facebook account. So this list also makes sense to me because lots of members of my living learning community in my freshman year are included in this list. But there are some random guys, so I just select them and remove them from the list. User can also add members to the recommendation results if they think the algorithm misses some members. So next is the third step. In the third step, we want to use to recreate some recommended lists they added in the previous step. So for example, I recreate the list LLC, and I select members and add it to the list. And the last step is the questionnaire. And when the user fills the form, the users can also view the recommended results. So we want to hear the feedbacks from our user. So when the users create and edit the list, the log records users' behavior, such as the mouse clicks, the timestamp of each actions, and also the members deleted or added to the recommendation results. So the data is in the following format. So the date and time and action and target, and then the detail. Some statistics are calculated from the logs we collect. We show this statistic in the visualization tool, but this is not the main focus of this presentation. So the reason why we have multiple steps in this part is that we want to verify the following hypotheses. The first hypothesis, the average amount of time to add a member to a list in step 3 should be smaller than step 1. The reason behind that is that in step 3, users just need to select the members provided in step 2. So it only takes the time of selection. However, in the step 1, user need to think about which user belong to which group before he or she makes the selection. Okay, so the second hypothesis, the average amount of time to create a list in step 2 should be smaller than step 3. So because in step 2, users just need to edit the recommended list, although they also have to spend some time thinking about whether this member belongs to this list. But we think the user will only make few additions to the list. But in step 3, they have to make selections of all the members in the list, which takes longer time. So here is the third hypothesis. The average amount of time to make an addition in step 2 is same as the average amount of time to make an addition in step 1. The reason is that in both cases, users have to spend time thinking about the member. And the last hypothesis is that the average amount of time to make an addition in step 2 is more than the time to make a deletion in step 2. So the reasoning is that it is easier to recognize a wrong entry than derive a right entry. So 5 Facebook users did the study, and here's the data we collect. So from the data, we can draw 2 conclusions. The first one is for the hypothesis 1 and 2. So users' data shows positive evidence that supports the hypothesis 1 and 2. We can see the average amount of time to add a member is smaller in step 3 than step 1, and average amount of time to create a list is smaller in step 2 than step 3. But however, for hypothesis 3 and 4, we didn't see the direct evidence to support that, because the reason is that the editor cannot precisely distinguish the time spent on different actions, so such as the time spent on additions and the time spent on the deletions. Okay, so next, I'm going to talk about the last part of the workflow. It's the performance and the visualization tools. But during this presentation, I'll only focus on the visualization part. So why we want to visualize it? So why do we want to visualize friend list? So actually, we have two goals in this part. The first goal we want to determine is the members of an actual friend list, so which is the user's real friend list in their Facebook account, are more closely related to each other than non-members. And the second goal is that we also want to verify this fact for the recommended list, so that we can compare the relationship inside the recommended list with that of the actual friend list. And in this way, and we can make a conclusion about how good is the algorithm. So how to visually compare the relationships inside and outside the friend list? So naturally, it's a network. So it's naturally to come up with an idea to use graph to represent users' friends. So for example, in this graph, in this application, I use the June graph framework, which is a Java library to develop this application. And you can see the blue nodes is a user, and the yellow nodes are the original members in the recommended list. And the red nodes are members deleted from the recommended list by the user. And the green nodes means additions to the recommended list. And the gray means other members. So from here, we can see it's very clear to represent the social graph. But there's a problem. So in the previous slides, the graph is generated from the fake data only for the development purpose. But actually, the number of friends of a Facebook user usually ranges from 200 to 500. For myself, I have more than 500 friends. So this application is now able to show, so the number is far beyond the capacity of this application. So this application is now able to show large social graphs, which means the actual user social graphs. For example, this is the real user graph. You can see it's totally unusable. So try to solve this problem. I developed a more capable graph tool by using d3.js library. So this is the data visualization library in JavaScript. So it has built-in functionalities to develop a nice graph like this, but it still has the same problem. So for actual graph, it's still hard to compare the relationship inside and outside the friend list. So what can you see about this graph? It doesn't provide any useful information. So finally, I tried the matrix representation to show the social graph. So in the adjacent matrix, cell Aij represents an edge from node I to node J. And the colored cell represents friendship, for example. So there are 10 friends from A1 to A10. So in A2 and A7 are friends. So the cell A27 are colored to mark this friendship. And also the A72 is also colored. And so we have this matrix representation, and the way we use to represent the friend list is that we have a friend set F, and we try to divide friend F into friend list and non-friend list. So which means we have a union of friend list and the friend set minus the friend list. So in the matrix, you can see the orange colored pixel. So they are the friend list. We sort the members of the friend list into the left upper corner. So they are all listed there, so you can see. So that way, all the orange pixels together, and for the other non-member relationships, we are in different colors. So d3.js also has built-in functionality to create the matrix like this, which is super nice. So the next, I'll show you guys some matrix about the actual friend list and some randomly generated friend list. So I'll ask you guys a question about. So I'll ask you to identify which one is randomly generated and which one is the recommendation result. Which one is the actual friend list. So here's your option A. Okay. And this is the second matrix. So anyone can tell the answer?
Is
Yeah, that's right, A's friend list. Because the reason is that the relationships are more dense inside actual friend list, and the matrix representation can show the difference in density inside and outside the friend list. So from here, like, we achieve the first goal. And then let's talk about the second goal. Let's verify if this fact also works for the recommended friend list. So I'll ask the same question: which one is the randomly generated list, and which one is the recommendation result? So here's your option A, and this is B. And what do you guys see? Anybody? So which one is the recommendation result? Yeah, definitely. So because we can see there are less like black pixels outside the group, which means like the relationships inside groups are pretty tight. And also you can see the density. The pixels are more dense in the matrix B. Okay, so now like we also achieved the second goal. The relationships are more dense inside the recommended friend list. So which means we verify the fact for the recommended list. So we can compare the recommendation result with the actual friend list to see how good the algorithm is. Okay, so here's the overview of the architecture of my project. First of all, we have a recommendation engine. It's a Facebook app. It collects social graphs from Facebook server and generates recommendation result and write the result into our department server. And this is the second component, is the friend list editor. So it loads the graphs and recommendations from our server, and it's displayed to the user as a Facebook app. And then the user can push the friend list back to Facebook. And this is the visualization tool. It loads the graphs and the recommendations from our server and generates visualizations for the researchers. Okay, so let's come to the conclusion of the project. So for the user study part, so we confirm the first two of the four hypotheses, and conclude that the algorithm can reduce users' effort to create the friend list. And for the visualization part, so we successfully visually demonstrate that members of friend list are more closely related to each other than non-members. And also the matrix representation proves its capability of demonstrating the relationships of friend lists, so which means it's better than the graph representation. And also, so which means researchers can use the matrix representation to evaluate algorithms. So some future work. So for the first component, the recommendation engine can be extended to do the multi-step evolution, which means you can, so for example, the current time is Ti, so you can trace back to Ti minus 1, Ti minus 2, or Ti minus 3, like this. And for the editor, we want to like extend the user interface to evaluate the evolutionary recommendation, and also we have to add some functionalities to distinguish the time spent on different actions to verify the last two hypotheses. And for the visualization tool, so we definitely want to visualize evolution recommendations to evaluate the evolution algorithms. So the future work will be completed by the new research assistant working with Professor Dewan in next semester, I think. So yeah, that's it. And also I want to give my special thanks to Professor Dewan and also Jacob Bertel, who is in California right now. So, any questions? Facebook is a friend list editor for the end user. It allows users to edit and view the recommendation result. And the third part of the system is called the performance and the visualization tools. So we designed this tool for researchers to evaluate the result and the algorithms. So let's start with the recommendation engine. So the recommendation system is a Facebook web app that mines the user's social graphs to make predictions on algorithms. So this is my approach. So I want to create a Facebook testbed that allows recommendation algorithm to be empirically evaluated. So the testbed consists of 3 components, and here is my workflow. So the first part, of the system is the Facebook recommendation engine that collects users' social graph and generates the recommendation result. So after we get a result, we go to the second part. It's a friend list. So it first asks users permission to collect their social graphs. So we keep all the data anonymous in the secure folder in our department server. So after collecting the social graphs, the recommendation system runs two recommendation algorithms. So the first algorithm is the group recommendation. So I use the hybrid click merger algorithms. This algorithm is developed by Professor Dewan and Kelly Bacon. So the friend list is that people do not take the effort to create the friend list, but they want the group-specific sharing. And so as computer scientists, we want to help users to reduce the effort to create friend list. And recently, there has some work on this topic. For example, it's Professor Dewan and Kelly Bacon's algorithm. So since we have had this algorithm, so the problem I want to solve is that, so how can we evaluate this algorithm? And I'm going to talk about my honor thesis project, a testbed for evaluating and visualizing Facebook friend list recommendation. And my advisors are Professor Prasun Dewan and his PhD students, Jacob Bartel. So by friend list, I mean reusable named groups, so which allow users to manage their friends into groups and perform group-specific sharing. So, but there's a problem with the reusable friend